Sriram Ramaswamy to start things off, and he's going to tell us about anti-diffusive phenomena in active matter.
First, of course, thank you very much to all the organizers for inviting me. The Newton Institute is probably my favorite science hangout place. I was here last couple of months ago. So many thanks. This program looks amazing and bewildering because we really are distributed across many disciplines. I mean, I suppose linked up in some way by an interest in hydrodynamic and layering phenomena. My talk title is just constructed to meet the requirements of the program. I hope you'll find it isn't actually misleading. That's where I am, that's my support. So let's get started. I guess it's okay if people have a pressing question. It's fine to interrupt while I'm talking. Okay, so given that this is about active matter, and given that, despite the impression of many people in the field, not everybody knows what it is, I'll spend a few minutes telling you about it. And I've taken the potentially calamitous decision of making this a Cook store of 3 sites where I think phenomena of the sort that belong in this meeting are implicated in some way. And I'll tell you about those, and then I'll summarize. Okay, so active matter is just the condensed matter physicists' way of incorporating living stuff into the domain of condensed matter. So you have a collection of objects. Imagine, take a living organism. It's made of cells, and each cell, takes up nutrient and uses it, and turns stored energy or ambient nutrient into work. And any such object is an active particle, and a collection of such objects we call active matter. And so a chunk of tissue is a chunk of active matter. A collection of organisms is active matter on a different scale, where each organism is the active particle. Go inside a cell, it's got large numbers of powered components, so the interior of the cell and the cytoskeleton and the motors running around on a different scale, that's active matter. And it's turned out to be useful to think of these systems in that light. The point basically is that each constituent particle has a built-in dissipative times arrow. As long as you keep providing it with free energy, it turns it into work. And these are the kinds of materials that we're interested in. And my interest has not been in making grand statements about biological function or anything like that. Really, as a statistical and condensed matter physicist, in what way is a chunk of stuff that's active different from a chunk of stuff with, let us say, the same spatial symmetries, but not active? So that's been one big part of the enterprise. I mean, in a sort of frivolous way, how is a collection of hot spheres at thermal equilibrium and a collection of a swarm of ladybirds, 2 different kinds of hot sphere fluids, different? Or how is a pit of snakes different from a dead polymer melt? And really, this has been the theme of a lot of active matter research, simply re-understanding mechanics, statistics, hydrodynamics for collections of objects like this. Okay. Apart from real live realizations of active stuff, you can make artificial ones. You could imagine taking a particle with a catalyst on one part of it, let's say, and immersing it in a medium in which there's a compound which, if you don't disturb it, stays in a high free energy state, but which, when it comes into contact with the catalytic bit of this particle, undergoes a decay. That decay means that on the surface of the particle, you have a solute gradient. Let us say there's more H2O2 here than here. And so you'll get surface flows, and this object will behave in many, and those flows will really be confined close to the surface, and this object will imitate the properties of, in some ways, of a ciliated organism or a squirmer. And it's been very successfully used by various groups to create collections of particles which, as long as you keep the H2O2 supplied, keep running around. At the level of an individual particle, clearly the motion will look on long time scales like some kind of diffusion, but it's very persistent, and more important, it isn't a time reversal invariant state. You can also make much sillier realizations of active systems, less well controlled but easy to handle in many ways. This is our group, or my colleague Ajay Sood's favorite system. You've got a surface like this, you're vibrating it up and down. I'll show you in more detail how that's done. It's vibrating rapidly. You put an object on it, and that object, let us say, looks like this in the sense that its two ends are different. And so this is the top view, you're looking at it from above, and you're shaking it up and down, and this thing is walking. So this object, given this vibrational energy that's being supplied, and its asymmetry and its coupling to the base, constitutes an active system. And you can put a large number of these particles down and make organized states. You can make flocks, you can make condensation happen, and so forth, as you will see. So, obviously the difference between a system like this one and this one is that you can say a lot about the sort of the statistical thermodynamics of a system like this because you understand these chemical reactions. The energy conversion process here is much coarser and can't be described as just a chemical reaction going from high free energy to low free energy. So you can't subject this to as simple a thermodynamic analysis, but apart from that, it's still a valid active system. Active systems, whether artificial or natural, have very interesting dynamical state diagrams. You can get condensation, you can get layering, and you can get turbulence in a wide variety of systems. That's not yours. Oh, it is, yeah. From bacteria in a liquid drop to motor microtubule purified systems in a container, to even a turbulent epithelium of dog kidney cells. Okay. So in that sense, active matter is a great place to look for phenomena like anti-diffusion, layering, and so forth. So in which sense, I dare say, my presence in this program is justified. The control parameters in these problems are interesting. You might have thought you look at things like temperature and density, but instead what you do is you look at, in this case, the labels seem to have disappeared. If you have an active object like the little Janus particle that I showed you, you can imagine it responding to external chemical gradients in two ways. One is that it reorients and then moves because of its intrinsic self-propelled character. The other is that, independent of which way it's pointing, it responds to the solute gradient and translates. So there's sort of taxis and phoresis, and I think that was taxis and that was phoresis. And in that plane, you can get a wide variety of behaviors, including some of the ones we're talking about here. As in any kind of particle plus, any kind of collective dynamics, because these problems are out of equilibrium, even the analog of a phase diagram actually depends on whether they are in a setting in which the total momentum of the system is conserved, that means object in bulk fluid, or whether they're sitting on a substrate. In the polymer dynamics language, this would be like Zim dynamics, and this would be like Rouse dynamics. In one case, the momentum is taken away by a sort of inert substrate. In the other case, the momentum is transmitted to other particles in the medium through an ambient fluid. So we call this wet and dry active matter. I should also say that as an audience, I assume, of hydrodynamicists, the general ideas of active hydrodynamics have been in the literature in various forms for many decades, but somehow didn't explode into a field until very recently. These fluidodynamicists many years ago talked about what in today's active matter hydrodynamics language would be called active model H. Those of you who know that. And more than that, of course, as you all know, in general, there's a long tradition of collective descriptions of objects swimming through a fluid, including PDEs not that different from the kinds that we'll talk about for the orientation and concentration of these systems. Anyway, okay, so the how do we build equations of motion for these systems? Very often, somebody gives you a generic system far from equilibrium. You say that, look, you know, what I'll do is I just close my eyes and write down anything that's allowed. And what I mean by allowed is anything that's consistent with the spatial symmetries of the system, right? You have a system that's in a driven state, therefore time reversal invariance is no longer available as a symmetry. You don't derive the dynamics from an energy function. You simply write down all kinds of allowed terms. But it's useful to view this in a slightly more precise way by noting that essentially any active system actually converts is an energy conversion system. Typically, a chemical reaction is proceeding in this direction. You can think of X as how much fuel is consumed, number of fuel molecules consumed. You can think of this as a spatial direction, and you know clearly any motor is something that you push this way, but because of its chemomechanical coupling, it moves not only this way but also this way, in the sense that its mobility in this abstract space is non-diagonal, right? And you can use this idea fruitfully to sort of justify once and for all this business of writing down terms, any term that is allowed, in the following sense. So let me just have the luxury of a long talk. Let me spend a little time on this. Supposing you had a system with some maybe coarse-grained momentum-like and position-like coordinates P and Q, and this other coordinate, this chemistry, X, then you can imagine that the effective dynamics of this system not only is governed by a Langevin equation in QPX space, okay, in which you've got the purely reversible part of the dynamics of Q and P. You've got the dissipative part of the dynamics of P. You've got a coupling between P and the chemistry, which in this language looks thus, right? With that coefficient entering with opposite signs in these two equations because it's a reversible coupling. Noise on the momentum, noise on the chemical coordinate, relaxation process for the chemical coordinate. So this at the moment is just dynamics at thermal equilibrium for Q, P, and X, with noises governed by a single temperature. If now you take, and what I've done with foresight is to argue that this chemomechanical coupling in general depends on the position, the physical coordinate of the system. So the moment, so am I making sense? Feel free to stop me at any point. I'm taking a slightly pedagogical approach to it, so you know, absolutely do stop if something is So if you do that, this at the moment, as I said, is simply fluctuating Langevin equation at thermal equilibrium. If now you choose to hold the force on the chemical coordinate constant so that on average the chemistry proceeds in one direction. So if you hold this guy constant, then the effective equations of motion of Q and P have what you might call a new term in the equation of motion for P. So new forces coming from you driving the chemical coordinate that way, and as a consequence, the momentum being pushed in a certain way. My argument is that generically, any, I don't know about absolutely any, but the big class of active dynamical equations that we look at all fall into this, in this broad category, okay? And the reason I'm going through this is not because I'm going to keep using this in detail with specific forms derived from some microscopic theory, but that this sort of licenses me from now on to write down very general equations of motion, including any terms permitted by the spatial symmetries of the problem, as the generic active dynamics of a given system. So I have a system. The advantage of this approach is that it has a point of departure, which is thermal equilibrium dynamics, and then you just decorate it with additional terms for which you sort of acquired permanent approval by this little process that I described. Okay, and I don't need to resort to an underlying energy function or something. I can just write down these equations from now on. Okay, so that's the introduction. This subject has been sort of active matter dynamics, active hydrodynamics has been around for a long time. This isn't going to be an introduction to all the results in the field. At some point, I'll use one or two key results and I'll try to rationalize them maybe by writing on the board. Okay. No questions. So it's either clear or completely opaque. Right. So let me talk about a system on which our group, and especially my friend and colleague Ajay Sood, have spent a lot of time working. It's a PhD work of Ajay's and my joint student Roshan, also earlier students Rahul and Harsh, who is now at IIT Mandi. The general idea is the following. So if you have, so this is one way of making active matter, which I described briefly earlier in the talk. So suppose you have a surface and you vibrate this surface up and down, and you have objects lying on this surface. Then when they come down, they'll typically come down one end or the other first. Imagine elongated objects. If they come down, if the two ends are similar, they'll just sort of tend to move back and forth, randomly back or forward or backward along their length. If the two ends are mechanically different in almost any way, if they're like this gadget with one skinny end and one fat end, or if the friction is different, or if the weight is different, you will end up creating an object which which converts your up and down shaking motion into walking. Okay? And really, it's what we remember from high school. If you toss an object up and it comes down, there's no static friction. The center of mass doesn't move. Therefore, in general, if there is static friction, it'll end up walking. Okay? And it does this, which I guess I showed you already. If there's a bare surface, there's a bare surface, it just follows its nose, and its nose does rotational Brownian motion as well on long time scales. You can also put the same object into a medium, as we'll see. This basic idea of vibration turning into walking was first done by Masaki Sano and group. They put a bolt in a track or a groove, and the bolt and vibrated it, and the bolt walked. So this cool idea has turned out to be quite fruitful. Okay, so the experimental setup, so I'll begin by telling you about some experiments. The experimental setup is this industrial shaker. The sample cell is about 10 centimeters across. The particles, the walking particles, are about half a centimeter in length and about 1 millimeter in diameter. The details of that taper happen to have to do with the type of particles that we could get, but it's important that they're tapered. There's a little bit of room here, which is why this particle can walk. That is, there's room for the particle to wiggle a little bit. We also look at another kind of particle, which is spherical particles. So these are heavy and made of brass. These are light and made of aluminium, if I remember right. And we look at the system with a camera mounted above it. And it's vibrated fairly fast and a fairly tiny amplitude. Amplitude times frequency squared divided by acceleration due to gravity is about 6, I think, for the most part. Clearly, the amplitude itself doesn't matter very much because we have a system with a lid, and so you can't heat these things, you can't toss them up very high. But clearly, if you're at very low amplitudes or if you're at modest amplitudes, that makes some difference. And this vertical shaking means that, given that the particles aren't absolutely packed, you can think of two particles like this shifting slightly over each other as making them weakly, not quite hard particles, slightly penetrable particles. Okay, so this is a problem that this is an experimental system that we've exploited now for many years. And in earlier work, we showed phenomena like locking, trapping by external obstacles, interactions of two particles in an ambient elastic medium. But what we're going to talk about today is phase separation. So it turns out that if you work at a tiny fraction, even at a very tiny fraction of the rods, okay, so these guys, these elongated bits are the motile rods. These beads are the non-motile spheres. You can imagine that, when you vibrate something up and down, if you've got a sphere, it can't walk because the walking mechanism is based on tilting, and a sphere tilted is the same sphere. So it can't really do anything. So this is faint. As a function of bead concentration, if you keep the rod concentration at a very low value, and increase only the bead concentration, you go from essentially an isotropic state to something which in this picture is not very clear, but the movie will make it clearer, actually has velocity and orientational order of the rods, and then it starts to condense, and then eventually the rods assemble themselves into an active interface, which then condenses the beads off to one side, creating a state where there's high bead density here and low bead density here. The density contrast here is not huge, but it's still fun to see what they do, so let me show you. So this is the isotropic phase. This, if you watch and, to a parent's loving eye, is actually a flock. I can find you better movies. Here, they start to condense. But here, most interestingly, they self-assemble into an active interface. And this active interface, containing only a handful of particles, condenses a bulk quantity of the non-motile particles.
Excuse me. Can I ask a question?
Yeah.
Is there some reason why the container's that shape?
History. Yeah, so it's actually, at this point, it's an annoyance to us. At some point, we used this geometry, which was invented by Olivier Dauchot as a way of re-injecting particles back into the bulk. Meaning otherwise stuff tends to accumulate near the edge. Given that basically it's the deplorable fact that experimental systems don't have periodic boundary conditions, and so if you want to keep the particles away from the edge, you need some contrivance. This seemed okay, but for the most part, for many of the things we're talking about, it's not particularly important. Yeah, thanks for asking. I forgot that. Sorry, this should be, yes.
Is it important that all these particles move the same phase? Yeah?
So actually, they're not at all in phase, because you're vibrating something up and down, and even if you're tossing them up coherently, any slight differences in when they're launched. So they're not marking time it's quite incoherent, and I think that's important because I think you will start to get other interesting but not phenomena, but not relevant to this class of problems, like oscillons and other things. And actually, one is trying to stay away from them. In any case, when you have a lid, you do suppress most of that. Yeah. So this, I don't know why, yeah, okay. You can also do this in a channel geometry, again, unfortunately using this funny boundary, where you can see something which I may as well show you the model. Again, 5% rods, and you change the bead fraction from 20 to 50-something%, and you go from random to, you can see that it's actually ordered. There's a systematic circulation in one direction, and then eventually at higher bead fraction, the rods actually trap the beads. So you get something that's a lot like this class of phenomena of active particles condensing a passive core has been seen. This is Mike Cates, among others, on this work. And this is, if you like, a kind of 1D analog of that state. Okay, so can we understand, at least at a sort of infantile level of linear stability analysis, can we understand where this kind of instability might come from? So, well, you can write down a continuum theory of a continuity equation for the beads and for the rods. For simplicity, let's assume that the rods are only propelled in the direction of their orientation. Let's not worry about any independent diffusion. The bead velocity, okay, and the rod orientation relaxes, is reoriented by the velocity. Remember, this whole system is on a substrate. So we're not, you can have this term, which you can think of as like a weathercock term, says that if you've got a velocity in some direction, you reorient things with respect to that direction. Just like if you have a weather vane on a building and you have a wind, it turns. That's this term. The orientation also is sensitive to gradients in the concentration of the beads, and I'll tell you exactly why. Then force balance on the beads. I'm assuming that I'm working at low enough concentration of rods that really the bead density is the important thing. So the dynamics of the beads relaxes because of contact with the substrate. I could go to next order in gradients and give you a viscosity term if you liked. I've hidden all that in the dots. The beads get pushed out of regions where their density is high into regions where their density is low. And the presence of a local, that should be a capital P, I'm sorry. The presence of a local polarization of the rods impels the beads forward. Okay, so the rods, the polarized rods push the beads, and the rods have, I claim, a preference to point towards the beads. Now, this is purely empirical. Looking at the system, when you see what the rods are doing, what you find, you know the rods are pointed, so it stands to reason that it's easier for them to be accommodated with their pointy end in a high bead density region and their broad fat end in a low bead density. Okay? So, in fact, this turns out to be crucial, this combination. So I think the next slide has, yeah. So, rods like to point towards where there are more beads, and the rods power the motion of the beads. This combination means that you'll have rods moving like this, they'll create a bead density, an enhanced bead density in front of them, and they're happy sitting in a situation where they're pointing into that. So this is a feedback between rods creating an enhanced bead density in front of them and the rods being content to sit. All right. Yes, sir.
In addition to this problem where microorganisms consume some chemicals and create a gradient to which they're then...
Yeah. So these are all, kind of self-generated passive types of phenomena. Yeah. Yes.
What's the orientation equation, the polarization equation to denormalize?
No, it's a polarization field. It's an order parameter field, right? So it doesn't need to be unit or anything. Yeah, clearly, in principle, I should do more than this. I've hidden all the complications in dots. For example, there's two stories here. One is just this bit, rods pointing to beads and polarized rods pushing beads. If you just take that into account, you get an anti-diffusive instability, right? If this combination, if A times alpha is large enough in magnitude, remember, as I said, A is negative, you get a diffusively growing mode. Obviously, there are other terms in the equation which compete with it, but I think the core of the mechanism that gives you the instability that we saw lies here. There's also more. There's the interplay between polarization producing a bead velocity and bead velocity reorienting the polarization, which actually can give you flocking at very, very low rod fractions. This is something we discussed many years ago. And that can be folded into this analysis as well and giving you a slightly more complicated story. But I prefer to keep the story simple. So this is really the minimal understanding of what's going on. We have not tested, for example, whether it really is a diffusive growth. It all sort of takes place rather quickly, and we should. Now, the funny thing, though, is there doesn't seem to take very many rods to make any of this happen. So in particular, you get a phase-separated state that looks like this. This is, again, rather fun, though. So notice you can hardly see the rods. There's a handful of them, but you wait, and they sort of self-assemble into a piston, which then, moves all this stuff along. So there's two questions. One is why they orient and self-assemble, but the other is how it is they're able to push this much stuff. Excuse me. Shut down the computer. So we did a little analysis of this, a one-dimensional analysis, where we, remember I said that there's a damping. That damping will, of course, just, the rate, since each particle loses momentum at a certain rate, loses velocity at a certain rate, the collective damping will be proportional to the density. So the force balance you can write as damping times the velocity is the gradient, this is the bead velocity, is the gradient of some kind of bead pressure. And let's say it's being forced by this little concentrated bit of rod stuff, and the beads are conserved. And let me unwrap this and think of this as a one-dimensional infinite system with some density rho naught at minus infinity and moving along. And you can then solve this problem. It's analogous to what Madan Rao and group did for what they called plowing through a dense bead medium or something like that. And you can solve them. What you find, roughly speaking, is that ahead of the rods, you get a decay of the bead density, which is rather slow, because it depends on the effective compression modulus of this stuff, which can get very, very big. And behind, within an approximation where you sort of pretend that pi is just linear in rho, what you get is a concentration that's basically uniform. And so we haven't adapted this calculation yet to a periodic geometry, but basically what you get, therefore, is a moving front, a dense medium in front of it, whose density decays more and more slowly with distance, the denser it is, and behind sort of a uniform low density. And so this phenomenon of this, so the point, if you like, is that the reason that a tiny motile fraction is able to push all these guys is that there's sort of a non-local pushing through the fact that it's nearly impossible to compress this bead layer. So that's the end of this part of the story. So, I've shown you a novel kind of motility-induced phase separation, where a tiny motile fraction seems to be enough to create this phase-separated state. The analysis so far, what we've told you, I have told you a story without noise and so forth in it. We haven't, in the analysis, I haven't said what will happen when the rods will turn around. And I wouldn't swear that this mechanism, or even more, this phenomenon, can take place on arbitrarily big scales. I would have guessed that it's limited by the persistence length of the motile rods, I think. but we haven't been able to either see that in experiment or really do a serious calculation to show that. But that's the end of the first story. So that's, yes?
In the last experiment, was the density decays exponentially?
Sorry?
In the
I mean, if we measure, sorry, I forgot to add that graph. If you measure the density, it, to a sympathetic eye, there's a linear-ish decay and then it crashes. Because in any case, this object, it's only in the approximation where I treat the compression modulus as a constant that I'll get an exponential. And so, I mean, since we don't actually know the equation of state of this stuff, maybe if you put in something like hard sphere or hard disk, you'll get something. But it won't be quite exponential. It's more likely to be flattish. Okay, so that's anti-diffusion in dry active matter. I think I can manage this. Now I'll shift gears completely and talk about self-propelling objects in a fluid, but I'll talk about them in a limit where you've got these objects in an imposed ambient flow. I won't worry about the flow that the swimmers generate. I'll worry about how the flow reorients the swimmers and what happens. The motivation is caustics. A simple cartoon of a caustic from work by Wilkinson and Mehlig is if you look at phase space for one particle, then if at an early time the phase space distribution is like this, then these guys are moving faster and therefore there will come a time at which the distribution looks like this. And what that means is that the spatial density, which is the integral of the distribution over momentum, will get, in this simple picture, a 1 over root x singularity here. Basically, the idea is if you've got slow movers here and fast movers here, the fast guys catch up with the slow, and so you can get a divergent local density. As you all know, this phenomenon of caustics really originates in optics, where it's the envelope of reflected or refracted rays, and the accumulation of rays tangent to the caustic leads to a divergent intensity in geometrical optics. So our interest is in whether active particles without inertia but with persistence of motion thanks to their self-propulsion can do something similar. And we're not the first to ask this. Oh, that reference is not on here, it comes later. This general idea has been discussed by several groups, but what we did was to show, and this is Rahul Chhajwa and Rajashri and Rama Govindarajan, sorry, what was I saying? What we did was to study this problem in a simple model that I'll show you about. Obviously, if you've got motile organisms, any mechanism that enhances their encounters is important for many purposes, communication, reproduction, and so forth. So I'll discuss two simple models of this problem. It's important to note that even if the suspension velocity field is incompressible, the particle velocity field can have convergences through these mechanisms. Okay, so let's take a very simple model of a motile particle. Imagine you've got an object like this, a dimer with extension W, and let's make a really sort of childish model in which the equilibrium extension is 0. So W relaxes to 0, left to itself. W can be agitated, so you can think of this as a damped Hookean spring with no inertia, but to the extent that it is extended, it can be reoriented by flow. This is the symmetric and the antisymmetric part of any ambient velocity gradient. It can also respond to curvature in the flow. So if locally there's a quasi-like character to the flow, that provides a vectorial direction with respect to which this guy can orient. And this extension, to the extent that this object is extended and it is active, it has a motility. And that motility is here. It says that the position, the center of mass or centroid of this object is carried by flow, driven by external forces, and propelled by self-propulsion at a speed proportional to the extension. If we call this entire right-hand side the velocity of this particle, then this pair of equations can be rewritten as x dot equals v, and v itself acquires an equation of motion. So rather than w, the extension, being given an equation of motion, you can make it look like phase space dynamics for x and v, and written in the right form in which the right-hand side actually has the force on it. I've done it here for a constant force. You get an apparent mass, right? Because this is actually a force, the coefficient of v dot is the mass, and that mass is the relaxation time of the dimer divided by the mobility. Okay? This equation has many of the features of the Maxey-Riley equation. It doesn't have the more subtle features like the history term and so forth. The detailed form for a non-uniform external force field is too complicated to present here, so I won't bother. But once you have this form, you're tempted to think, look, this particle is exhibiting a kind of inertia. Will it then centrifuge out of regions of vorticity? Will it accumulate in regions of strain and so forth? So we studied it. You can non-dimensionalize it in, let's say you have a point vortex with circulation gamma, and you put one of these particles in that field, in that flow, and rewrite the equations of motion non-dimensionalized by the memory time of the dimer and this natural length scale made from circulation in that time. And you find centrifugal-like terms in the equations of motion. Okay? And you can study the dynamics numerically and compare this class of particles to what would happen with particles actually with inertia. These are non-self-propelled, but with inertia. These are self-propelled and no inertia of this simple type, which in the literature are called the active Ornstein-Uhlenbeck particle, because W is an Ornstein-Uhlenbeck process. And you see this pile up at a certain radius. You can monitor the number density as a function of distance. This is the initial density profile, and this is what happens after the dynamics has taken place. You do get what looks like a singularity in the concentration. For comparison, the inertial particle case is shown here. And if you look at distance against time, you find that is, each of these is the space-time plot of the position. And what you can see is if you're released later than at a large enough radius, you just go off. But below a certain radius, you accumulate. So the R versus T curves accumulate here. You get a caustic. You can work out, you can analyze it by looking at the inner and the outer solution, look at small r and large r. And you can derive the shape of this boundary in the small r in the inner region. And it agrees with what you measure numerically. You find that beyond a certain initial radius, there are no caustics. And in the outer region, you can argue that R double dot is unimportant, and therefore the velocity is a well-defined and non-singular function of R. So beyond a certain R, there's no caustics. You can also repeat this for a more realistic active particle, namely an active Brownian particle in which the extension vector has a strongly preferred length. The detailed dynamics is different, but similar features obtained there as well. And you can also now, instead of one vortex, you can strew a bunch of independent active particles in a medium filled with two-dimensional turbulence generated by solving Navier-Stokes. And you can, the important control parameter, if you like, is, you can think of it as the speed divided by the background speed, or the, yeah, that's good enough. You can measure a quantity called the Okubo-Weiss parameter, which is positive in vortical regions and negative in straining regions. What you can do is you can ask, how does, if you look at where the particles are, what does Okubo-Weiss look like in those regions? Now, what you find as a function of that polar flow coupling and self-propulsion is there's an optimal range of self-propulsion. If you move too slowly, you just get carried by the flow. If you move too fast, you ignore the flow. And there's a sweet region in between in which you get a maximum accumulation of particles in the straining regions of the flow. The effect is, remember I mentioned that there's this polar, where is it gone? Yeah. This is the place in which the fact that this object has a polarity really enters. That's this coefficient. And that coefficient really makes a difference. It turns out really that increasing the polar flow coupling greatly sharpens the accumulation of particles in the straining regions. You can go through and look at where the particles concentration is localized. The black dots are the particles, the color is the local square of the velocity gradient. And you can measure this quantity. What you do is this. You look at where you look at the Okubo-wise parameter and its distribution in regions where the particle concentration is high, and what you see is that at low activity and at high activity, it has a lot of weights to the positive side, but saying it right, excuse me. Yeah. Yeah. So you get accumulation in straining regions at intermediate values of self-propulsion. Okay. So I hope I've convinced you that active particles without inertia can do things that passive particles with inertia do. They cluster in straining regions and turbulent flows. There's a sort of optimal level of activity. There's many questions that remain, really working on the consequences for enhanced encounters, and even asking whether maybe advection by active turbulence itself could accomplish phenomena like this. I don't know. Okay, now let me move to part 3. This is now sort of the full mess of the hydrodynamics of active suspensions. Okay, this is the PhD work of Purnima Jain, who's a student of Prasad Perlekar's, and Navdeep, who used to be a student there, who's now at Göttingen. You have all seen flocking models. Basically, if you've got self-propelled particles that stay apart, don't come too close, don't go too far apart, but tend to align with each other by lining up with the average of their neighbors, then at low noise and or high density, you get a flock. This analysis was done without worrying about an ambient fluid. What we showed many years ago is that if you include the hydrodynamics of the ambient medium, then in the Stokesian limit, at large enough length scales but still remaining Stokesian, flocks are always destroyed by flow. And the result is this spectacular active turbulence that many groups have looked at. This is a picture from Zvonimir Jogic's group. I will not spend any time explaining the mechanism. It's hidden behind this picture. Okay. What we showed much more recently, a couple of years ago, with many of the same people in that picture, and Ryan Chatterjee and Aditi, is that inertia rescues you from this seemingly inevitable instability. Okay? So if you want, the important dimensionless parameter, it turns out, is this ratio. You can think of it as a ratio of the self-propulsion speed squared to another speed, which is the characteristic active stress divided by the mass density. Stress over mass density is a squared velocity. V0 squared is a squared velocity. V0 tells you the swim speed, sigma A over rho, square root thereof, tells you the speed at which the instability that I talked about actually invades. So the fact that this parameter matters, it tells you about the possibility of outrunning the active instability, outswimming is the active instability. Okay? And what you see is this interesting dynamical diagram. This is a parameter we won't worry much about. It's the ratio of orientation. It's the ratio of the orientational collective diffusivity to the kinematic viscosity. So most ordinary molecular or colloidal systems are way over here. As a function of this inertia parameter, you go from down here, the original Stokesian active turbulence to a regime of defect turbulence, then into, again, a regime that's still unstable, but now with a growth rate of order q squared, in which tendentiously I could associate with a kind of anti-diffusion. That's not what I'm going to talk about. All I want to say is that if this parameter is large enough, then you will be in here and you'll be absolutely stable. Okay? So this part of the story is just to tell you that we will not, in the remaining 6 or 7 minutes, worry about the active instability driven by active stresses. We'll assume we're working at large enough values of this important control parameter, that is large enough self-propelling speed, that the original active instability due to Sima and myself is gone. But this analysis was without the concentration field. What happens when you include the concentration field? Well, let's first look at what happens at orientation and concentration when you don't have a hydrodynamic velocity field. That's the Toner 2 model. If P is the orientation and C is the concentration, you have a free energy functional favoring or an ordered state with P. You have a natural coupling of the vector orientation to concentration gradients. You can think of it as a kind of scalar flexoelectricity if you want. The orientation advects itself and relaxes in the molecular field due to this free energy functional. And the concentration is transported with a speed proportional to the local vector orientation. If you take the system and study its dynamics in the ordered phase, then the concentration and the transverse components of the orientation beat against each other and give you waves. Now, what happens to this scenario when you include an ambient fluid? So now we're not worrying, as I said, about the classic instability of active fluids. We're worrying about how fluid flow affects what you might call the Toner 2 waves. Okay? So for that, you have to write down those same equations, but now you have to include the coupling of flow to the orientation. That's the symmetric and the antisymmetric part of the velocity gradient. You have to allow flow to advect the order parameter, not only the order parameter to advect itself. You have a momentum equation. We will not worry about the active stresses, but we will include here an important stress arising from this term. So it's a little complicated to explain, but basically, in an anisotropic active system, you can have forces proportional to the concentration gradient, but anisotropics, they are not pressures, right? It just means that if you have a local concentration gradient, you can have flow generated by that in a, it contributes to deviatoric stress. Okay, there's nothing active about this. It's just saying that local concentration orients the orientation, local concentration orients the orientation. So now the point basically is here you had concentration gradients affect orientation, orientation affects concentration. Here you have that physics in these two equations, but you also have stresses due to concentration gradients affecting fluid flow, and the fluid flow reorients the orientation. So the orientation can respond either directly, like in a dry active matter system, or indirectly via the intermediary of the hydrodynamic velocity field. And these two things don't take place on the same time scale. And what we found, to be very clear, what Purnima found, is that you get, for splay perturbations, you get a mode whose real part of the frequency is basically the waves that the Toner 2 equation would predict. You have relaxation due to concentration diffusivity and collective orientation diffusivity. And you have this very strange term. This term is proportional to the inverse of the orientational mobility. That object is actually, gamma is roughly of order 1 upon a shear viscosity. So you have what looks like a viscous term, because it's really basically mu over rho times polarization and times the flow coupling, with the wrong sign. So something looking like a viscosity is ending up destabilizing flock. So here's your anti-diffusion. The physical picture really is, and I can only say it in words, I don't have a good cartoon. You have two kinds of orientation response. Direct, as in dry flocking models, and indirect through fluid flow. If you went to the Stokesian limit, the velocity field would kick in instantly. This dynamics is gone, there's no lag. With inertia, the velocity field lags. So you've got the orientation and concentration dynamics, and as this thing is kind of relaxing, the velocity field comes and kicks it again. And what you get is movies. This is the concentration of the velocity, and you can see there's sort of a joint dynamics, which maybe is not so enlightening. The important control parameter is this coupling between polarization and concentration gradients, that coefficient E. Okay? We're working in the regime where the polarization likes to point away from high concentration. So we are not working in the regime where the system wants to condense. It's not motility-induced phase separation. It's stable as far as that goes, but what you find at modest values of the parameter E is the color code is the concentration and the arrows are the orientation, and you get sustained, quite orderly traveling waves that keep going. So its system makes its own waves, so there's an oscillatory instability. The characteristic wavelength is actually, roughly speaking, the following. You can think, you know, when you've got sound waves and viscosity, you can ask for a length scale above which the sound is underdamped or below which it's overdamped. It's roughly a combination of that sort. This is essentially the splay concentration wave speed, and this is the kinematic viscosity. And you find these modes with this dominant wavelength at low values of E. As you increase the coupling, you enter a regime where now you're starting to see disorderly behavior. The arrows again are the polarization and the color is the concentration. And at still larger values of the coupling, you really get a concentration wave turbulence. Like this. So that's regular and chaotic anti-diffusion. One fun fact with which I'll close is that if you look at this system, the kinematic viscosity is much larger than diffusivity, and so you're in a situation where on big length scales, what you have is a stochastic velocity field carrying the concentration, and because you're at large Schmidt number, Batchelor would tell you should get a certain scaling of the concentration spectrum. The numerically measured concentration spectrum has a form which, at least to a sympathetic eye, agrees with that. So you get an interesting contact with passive scalar advection physics. Okay, so I'll summarize all three parts. One, a new route to active-passive segregation, where an active interface condenses a passive bulk. Two, caustics without inertia, but with motility. And three, active turbulence without active stress. Thanks, I'm happy to answer questions.
Thank you very much. Got time for some questions?
So I'm wondering, in the first part of your flow, whether you get more insight into the dynamics or maybe what the model equation should be, if you expand and have a couple more control parameters. So for example, if your beads, if you changed the radii or the density of the beads, it would control damping. And the reason I ask that is your talk suddenly brought forth a memory from when I was about 12 years old. At that time in America, that's the early 60s, there was suddenly a popularity where all these games had vibrating tables, like little American football players moving around, right? They were your elongated asymmetric particles, and you really wanted them to cluster. So somebody in my friend group had the idea of filling the rest of the field with little buttons, not beads, but buttons, with different radius and different masses. And we certainly saw big effects, but we didn't know what a bifurcation parameter was as 12-year-olds.
Cool, I didn't know what this, so that there are sort of self-propelled football tables.
See, they were really popular from the late 50s and early 60s.
Cool. We could, one of the things is, for best results, it turns out it's important that the beads be light compared to the rods, then they can be pushed around. Varying the diameter poses an experimental nuisance because everything, you have a fixed gap, and if you make the beads very small, you'll get heaping. So one has to think a little bit about exactly how to do this. Worth playing with, yeah. Yeah.
The last simulation you showed, which had that turbulence in some variable, can you just show it again?
Yeah, sure.
I'm just curious why you call it turbulence, because it doesn't look very complicated.
Initially it wasn't. So here it's actually orderly. It's actually, it's a self-sustained periodic oscillations. And if you look at frequency wave number space, there's a well-defined frequency and a well-defined wavelength. As you increase that control parameter, the coupling of polarization to concentration gradients, you start entering a disorderly regime. You start seeing vortices, you start seeing a disruption of the ordered state. And then here it is sort of self-stirring and no longer ordered. The macroscopic polarization order is actually lost. So in that sense, it's like active turbulence of other kinds that have been seen in these problems, but driven by a different mechanism. So it's turbulence to that extent, and you can measure various spectra, and as people have seen, many people in this room have worked on this problem more than we have, there are, you're welcome to not call it turbulence in the usual sense, but it is, as far as I know, a spatially chaotic state, and it has statistical features that are reproducible. That's really what it is. And in this case, a good deal of vorticity in the polarization rather than velocity. Yeah.
Yeah, there is a question about your Royden beads experiment. You had this case with a circular channel, and you showed how we get this sort of crystal of beads forming. I was wondering, so this crystal can move either clockwise or anti-clockwise. I was wondering how that choice is linked to the initial Poisson noise in the orientation of the road.
I mean, the point is, it's absolutely, it picks one, and if you repeat the experiment, it won't pick the same one by any means. So it's, there doesn't seem to be any bias in the experimental setup there. It's pretty even one way or the other. That's equally true for the earlier flocking states we saw. Basically, in all these problems, once you confine to a closed quasi-1D geometry, what was two-dimensional rotational symmetry breaking just becomes a sort of easing clockwise versus anti-clockwise symmetry.
So can you give maybe a simple physical explanation of why active particles tend to cluster in the high strain regions in the 2D flow? And I mean, it must depend to some extent on how active they are. Right?
Yeah, they do. I think the point is this. Within, to some degree, the equations of motion for the active particles can be made to look exactly like the equations of motion for particles with inertia, which are known to get centrifuged out of vortical regions and clustered in strain regions. So because persistent motility imitates mechanical inertia in some ways, that's the reason why, that's one way of seeing why it happens that way.
So the zero inertia case looks like something that would just be expelled out of the cells, is what you're saying.
Yeah, no, I'm saying here also these have zero inertia, but their velocity, their self-propelling velocity has a finite memory. Right. And therefore they act as though they have inertia. You get an induced apparent inertia. That's roughly the reason.
Yeah, thanks.
Yeah, I had another question about the one where you had the plug filled the channel. Presumably there's a couple of other parameters or other things that are interesting there. The rod density presumably makes a difference there. So if the density isn't enough to fill the channel, what
yeah, then. So I mean,
does it still try and make it a little?
They try, and then it's sort of, but it's you do need enough to fill the channels. So I mean that's sort of a dirty secret which I wasn't showing. But yeah, yes.
Is there also a kind of a boundary? I mean, what are your boundary conditions? Because presumably the boundary has a polarization effect, right?
Yeah, I mean the point is these rods tend to at least in these experiments, often they tend to lie parallel to the boundaries. But sometimes normal, and then that makes a bit of a mess. So there are some, they don't, no, I guess, okay, so on the whole, at enough rods that you can just even make one row, it pretty much finds its way to this state. And lines up like this. It's kind of cool.
maybe a related question. In this simulation, is compressibility necessary or?
Compressibility of the solute, yes, because it's a concentration field.
Yeah.
But the suspension velocity field is incompressible.
U doesn't have to be compressible.
U is not compressible. Yeah. I mean, that would be sort of a, for the kind of experimental systems we're thinking about, it wouldn't make sense to really make U significantly compressible.
Any more? No? In that case, we'll break for coffee, but let's thank Sriram again.